So if you remember all the way back to last Wednesday, what we had discussed we're kind of wandering around in 1.7, and today we'll maybe get to 1.8. They're very similar sections. We were discussing direct proof and proof by contrapositive. So the way of going about a direct proof is we want to prove something like P implies Q. We want to show that P implies Q is true. And the only way that a statement P implies Q is false, so when is this false? And can someone remind me?
When P is true and Q is false.
Exactly. This is only false when P is true, Q is false. So you show that this scenario never occurs. So to show P implies Q is true, show that this never occurs. So you assume P is true, and then you show that that forces Q to also be true. So you're never put into this situation. So P implies Q is never false. And then we did kind of very similar things where if you want to show P implies Q is true, what does the contrapositive tell you? What's something that's logically equivalent to P implies Q?
Not Q implies P.
Yeah, thank you. To all of you who responded very quickly. Not Q implies not P. So as we noticed sometimes, the direct proof strategy for some P implies Q doesn't always yield helpful statements, but something that you can always try is you can always try to show that not P implies not Q is true, because these two statements are logically equivalent. And sometimes it's easier to go in the other direction. We saw this in particular when we were trying to prove things about irrational numbers. It turns out that you can't really say anything like constructive about irrational numbers, except that they're the opposite of rational numbers. So then it makes sense that you'd want to use the contrapositive to get a new statement that's not about irrational numbers, but rather about rational numbers. And then you can, proceed. So let's do one more example of a proof by contrapositive. So just as a warm-up example, prove that if m and n are integers, then m times n is even if and only if, or no, I don't want to do if and only if. Sorry. If m, prove that if m and n are even, mn is even if m is even or n is even. Okay, so what we have is so if we break this down, this is saying E of mn implies, let me see exactly, then m is, yeah. E of mn implies E of m or E of n. This is the thing that we're trying to prove. Evenness of a product means that one of the two things is even. How would we use the contrapositive to prove this? First of all, what is the contrapositive of this statement?
Would it be not E of m and not E of n?
Exactly. to get the contrapositive, we negate propositions and this is a compound proposition. And so we use De Morgan's to simplify this proposition here. So we get not E of M and not E of N implies not E of M times N. And this ends up being more helpful because saying that M times N is even just says, well, M times N is equal to 2K for some K. But this, once we can say this, we're a little stuck because this doesn't directly tell us anything about M or N separately. Whereas over here, this is the proposition that M is odd and N is odd, and then we're going to be able to say something about M and M times N. So do we see how this direction is a more productive approach to the problem than this direction? This is all scratch work, by the way.
Is the E in front of the M's and N's supposed to signify even?
Yeah, I should have mentioned
Okay.
that. Yeah. Any questions? Any further questions, I mean? Okay, so now that we have kind of concluded that the contrapositive approach is the better way to go, then now I can write a formal proof. So proof, we use the contrapositive, or we use proof by contraposition. Whenever we don't use a direct proof, we should include what kind of proof we are using. So we assume M is odd and N is odd. What can I do if M is odd and N is odd?
Can you write their definition, like M and N equal to K plus 1?
Exactly.
And
By
K is an
definition, sorry, I didn't mean to cut you off. But yeah, that's exactly correct. By definition, we have M is equal to 2K plus 1 for K in Z, for some K in Z, and N is equal to 2K prime plus 1 for K prime in Z, right? Here we have to introduce two variables because there's no guarantee that K and K prime are the same. But then M times N is equal to 2K plus 1 times 2K prime plus 1, which is equal to 4K K prime plus 2K plus 2K prime plus 1, which is equal to 2 times K prime plus K prime plus 1. Thus, Mn is odd. QED. I think that this was, I mean, the proof by contraposition is really just a direct proof when you are switching around, you're using the contrapositive on the implication. So I think that this shouldn't be too strange to y'all. Like this? Yeah, so any other questions? You're all feeling pretty comfortable with proof by contraposition at this point? I mean, barring having done examples yourself, which is always the most helpful thing.
I just have a question.
Yeah, sure.
When you factored out the 2 here, why is there no 2 in front of the 2k, k prime?
So I have a 2k plus 2k prime, right? So since the k and k prime are probably different, I just treat them differently. So if I oh, you're right. Thank you so much. This is where
Okay,
you
yeah,
were looking.
no
Yeah,
worries.
that's
Okay, cool.
absolutely correct. Thank you. I'm
Okay,
sorry.
yeah, no problem. Thanks.
Good catch. Any further questions? Okay, great. Now we're going to come to a much more interesting proof method. So here's proof by contradiction. So here, this setup is the following. We want to show that P is true, some proposition P. And this could be a more complicated proposition like P implies Q. That's fine. So we want to show some proposition P is true. Then one thing that we can do is in the framework of our logic, what we can do is we can show that not P implies false is true, right? So here false is the contradiction statement, right? Where you have a tautology is a statement that's always true and a contradiction is a statement that's always false. So if not P implies false is true, then what does that force the hypothesis to be?
False.
Yes, exactly. If maybe I'll write it, Q implies F is true, the hypothesis must be false. Q must be false, right? Because if I had a true implies false, then the implication as a whole would be false. If the implication as a whole is true, but the conclusion is false, the hypothesis must be false. So if we're able to show that not P implies false is true, then not P must be false, which is equivalent to P being true. Sounds a little heady perhaps at the beginning, but we'll do plenty of examples. So often what we end up showing is something of the following form. If we want to show P, then one way to do it is show is true. You can show not P implies R and not R for some proposition R. Right? We know that contradictions can be constructed out of basic propositions in this form. R and not R is false. So this is the same thing as not P implies false. So this is essentially the proof strategy. You take the negation of the statement that you want to prove and you show that you produce a contradiction from that. Okay, so let's do some examples. So here's the first example. Let's show that n cubed plus 5 is odd implies n is even. Okay, so in this case, this whole thing right here is P, or in other words, O of n cubed plus 5 implies not O or E. I mean, it doesn't really matter. I'm just writing it out this way. E of n. This whole thing right here is the proposition P that I want to prove to be true. So what do I do in order to work on this sort of thing? If I'm trying to prove P, what does a proof by contradiction start with? Well, it starts with assuming not P and then trying to produce a contradiction. Sorry, someone was saying something? Is there a question?
No, I was just saying what you were saying because you asked the question.
Yes, I should have waited a little longer, sorry.
It's okay. I had my mouth full of grapes.
So, very good. Yes, we're taking this and we're going to assume its negation. So what is the negation of an implication?
Do you have to change it to the implication substitution, or do you not have to do
Yes,
that?
very good idea. I think that's what I want to do. So I want to say, well, P, this proposition, this implication, is equivalent to not O of n cubed plus 5 or E of n, right? And then what's the negation? So P is equivalent to not, or now I'll write E of n cubed plus 5 or E of n. And then what's the negation of this? Yeah, it'll be P and not Q is the how we negate an implication, but as we see here, it'll be not E of n cubed plus 5 and not E of n. And if I translate this back into my original statement, this is the statement that O of n cubed plus 5 and not E of n, or and O of n cubed plus 5 and O of n. So maybe this was, I mean, this wasn't too complicated, but the idea is if you want to negate an implication, you take the hypothesis and the negation of the conclusion. So what I want to do is I want to do proof by contradiction. Assume that n cubed plus 5 is odd and that n is odd. Right? So the first thing that I do when I am trying to use a proof by contradiction is I contradict or I negate what I'm trying to prove. And in this case, that leads me here. Well, if n is odd, then what can we do?
Set it equal to 2k plus 1.
Perfect. N is equal to 2k plus 1 for k and z. And now I can compute this thing right here. So then n cubed plus 5 is equal to, well, 2k plus 1 cubed plus 5. And now we're going to have to do a little bit of math. So 2k plus 1 squared is going to be 4k squared plus 4k plus 1 times 2k plus 1 plus 5 is equal to, now all the way out, 8k cubed plus 8k squared plus 2k plus 4k squared. Oh, I should write it over here. Plus 4k squared plus 4k plus 1 plus 5, which is equal to 8k cubed plus 12k squared plus 6k plus 6. Did I do this math correctly? I believe I did, but I'm very open to someone correcting me. But here, this is equal to 2 times 4k cubed plus 6k squared plus 3k plus 3. And this is an integer. So what do I conclude from this?
N cubed plus 5 is even.
Thus, n cubed plus 5 is even. That's what I get from here. And from the assumption, n cubed plus 5 is odd. Here is my statement of R and not R. This is a contradiction.
How are they both?
So it's not possible for something to be both. The point is that this statement that an integer is both even and odd is a contradiction. This is always false. So what I've shown is that if I assume the negation, so if I assume that n cubed plus 5 is odd and n is odd, then something breaks. I then get that some number is both even and odd. So this assumption that n cubed is odd and n is odd has to be false. So what we showed was this. We took not p, in this case, not p is the statement n cubed plus 5 is odd and n is odd. And what we showed is that n cubed plus 5 is even and n cubed plus 5 is odd. Since this statement is false and this whole thing is true, not p has to be false. Or in other words, the statement n cubed plus 5 is odd and n is odd is false.
Okay.
But this statement being false is the same as p being true, which is n cubed plus 5 being odd implies n is even. It may feel a little circuitous right now, and admittedly, this problem could also be solved via contrapositive, but I wanted to use it as a preliminary example for how we use proof by contradiction. Any other questions? Still a little confusing, probably? If so, that's fine because I've got more examples. But before I move on to another example, are there any questions here? I know I've already asked, but I, want to give some time to digest. Okay, let's do another example of proof by contradiction. Example. Show that 3 of any 25 days must fall in the same month of the year. So essentially what we're saying here is that You pick 25 days out of the 365 days of the year, and if you pick 25 days, then there must be 1 month that contains 3 of those 25 days. So if we want to use proof by contradiction, how do we contradict this statement? Right, we would say that no month contains more than 2 days, or in other words, assigned to each month, or each month has less than or equal to 2 days assigned to it. So we use proof by contradiction.
Why would it be 2 days? Is it just because two is less than 3?
Yeah, exactly. Less than or equal to 2 days. So here this is saying that, sorry, let me focus the camera again. This is saying that if you pick 25 days, then 3 of them have to be in the same month, that some collection of 3 has to be in the same month. To contradict that, or to negate that proposition, you say, I'm going to pick 25 days, and each month is going to have less than or equal to 2 days. Do you agree that that is the negation of this proposition?
Yes.
Right. Here, technically, this is there exists statements, and then I am doing a negation. This is like there exists a month such that 3 of the 25 days fall in that month. And my negation is that for all months, it is not the case that 3 lie in that month, which means that there are 2 or less in any given month. Proof by contradiction. We assume 25 days are chosen such that each month has less than or equal to 2 days, 2 of the days. Okay, but if each month has 2 or fewer days chosen, then how many total days have I picked? Yeah, exactly. It's less than or equal to 12 times 2. Thus, 24 or fewer days have been chosen. Wait, have I not had the light on this whole time? I'm so sorry. Have been chosen. And 25 days have been chosen. This is a contradiction. Okay. So is this second example a little helpful? Here, what I'm trying to prove is that if you pick 25 days out of a year, then 3 of them have to fall in the same bin, so to speak, where the bins are the months. If I want to contradict that proposition, I say, well, I'm going to take 25 days, but at most 2 fit in any given bin. But then I count up how many days that leaves me with, and it's less than or equal to 12 times 2, because I have at most 2 days fitting in any given bin or month. So then I have picked 24 or fewer days, and I have picked 25 days. And this and this are, they can't both be true, so I have produced a contradiction. Thus, this proposition must be false. And if this proposition is false, that means my original proposition is true. at the very beginning of class, I remember talking about logic and why we needed to have a logic system that can handle false statements. And I think proof by contradiction is an excellent example of how we use a logic system that can treat false propositions to prove true things in mathematics. Any question here? No questions? Everyone is very comfortable with proof by contradiction so far?
I have one question.
Yeah, sure.
Is saying that this is a contradiction just the same thing as P implies false or not P implies false?
Yeah, exactly. So essentially what I have done is, if I want to show P is true, what I show is that not P implies false is true. Thus, not P must be false. So P is true. And where the proof ends is by showing that not P implies false. So that this stuff is just kind of not said, but understood when people are reading proof by contradiction.
Okay.
Helpful?
Yes, thank you.
Yeah, sure. Okay, now we come to a very exciting point in class. Because here comes a very fun proof, maybe one of the first examples of a proof by, first example of a proof that had serious real life ramifications, because someone was murdered over this proof. We're going to come to the proof that square root of 2 is irrational. Okay, before we get directly to this proof, I want to make a comment. We need a fact for this proof, or fact. For a rational number, which can be written as P over Q, there is a notion, a lowest terms form. And this essentially means that you divide out by all the common factors. So essentially, this is very familiar to you. This says that if you have 27 over 3, well, this is a rational number. This is a valid rational number, but this is not its reduced form, right? Because the top and bottom have a common factor. What's the common factor?
3.
Right. So what other rational number is this actually equal to?
9 over 1.
Right, 9 over 1. Or similarly, if I pick something more complicated, I can do something like, I don't know, 18 over 90, right? Here, these should both have common factors. Namely, once again, a 3 divides both of these. So this is the same thing as 6 over 30, which is the same thing as, well, 6 divides both of these, so this is the same thing as 1 over 5. And so here, in both of these cases, we can always take any rational number and write it as a different rational number. Well, technically it's the same rational number, but it's written in lowest terms, so the top and bottom no longer have any common factors. So we're going to use this fact that we can always find a representative of the rational number where P and Q have no common factors. Any question about this? Okay. So let's prove that square root of 2 is irrational. And what we're going to do is we're going to prove it by contradiction. This is a very reasonable thing because saying something like it's difficult to do something with an irrational number, but we can do something immediately with a rational number. So this tells us that the statement that we should be working with is square root of 2 is a rational number, and that means that our proof method should be contradiction, because we're going to explore the negation of the proposition that we're interested in. So proof by contradiction. The way that we start proofs by contradiction is we assume the negation of the statement that we want to prove. What's the negation of the statement that we want to prove?
Square root of 2 is rational.
Yep. Assume square root of 2 is rational. By definition of rational, what can we do? Yep, we make it a fraction. Square root of 2 is equal to P over Q for P, Q in Z, and Q not equal to 0. Okay. So now what I'm going to do is the following. Moreover, we can assume that P and Q have no common factors. In other words, we can assume that we have written this fraction in its kind of reduced form. And this is the statement that we're going to use to produce a contradiction, okay? We're going to be contradicting this idea that P and Q have no common factors. So currently we assume P and Q have no common factors. Let's do some algebraic manipulation and see what we get. So if square root of 2 is equal to P over Q, then Q times square root of 2 is equal to P. So what happens if I square both sides?
You get Q squared times 2 equals P squared.
Yep. Now, what can I conclude about the number P squared from this? Yeah, it's even. Thus, P squared is even. Now I do another thing. If P squared is even, what must be the case about P? Can P be odd?
Yes.
An odd number times an odd number will give you back what kind of number?
An odd number.
Right. So if P squared is even, P has to be an even number.
But if P squared equals Q squared times 2, and anything multiplied by 2 is even, then wouldn't P squared be even?
Right.
Or is that
So
the point? We're saying that it's P squared is even, but P squared is an odd number.
So we're not saying anything about P squared being odd. All I'm saying is that from P squared being even, we must have P being even. In other words, there's another fact that I'm using, which is that n squared even implies n even. So I'm using this fact, and then what I was explaining is, why is this fact true? You can prove this by contraposition, right? The contrapositive of this statement is n is odd implies n squared is odd, which is true. So that I'm just justifying why, if p squared is even, we must have p even.
Okay.
Right. Okay, so if p is even, then what can we do?
You can divide it by 2.
Or in other words, I can write it as a multiple of 2, right? P is equal to 2k for k in z. Great. So then we have q squared times 2 is equal to 2k squared, which is equal to 4k squared. So essentially what we showed is that we assumed, we noticed that p squared has to be even because it's divisible by 2. But any time that a square is divisible by 2, it's actually divisible by 4. There's no way that you can find a square that is divisible by 2 but not divisible by 4. That's essentially what is being used here. And then I'm just writing that. So not only is p squared divisible by 2, but p squared actually must be equal to 4k squared. But this implies, if I divide by 2 on both sides, that q squared is equal to 2k squared, right? I've just divided both sides by 2. What can I now conclude about q squared? Yeah, exactly. Mahita, you're even further ahead. This implies that, so thus, q squared is even. And by the same argument above, and by the same argument as above, q is even. Because if a square is even, then the base of the square must be even. Okay, so what have we concluded here? Q is even, and also P is even. If P and Q are both even, then they have a common factor of 2. But we also assumed that P and Q have no common factor. This is a contradiction. Well, you know, so what happened was there was a group of Greeks who followed Pythagoras. They were the Pythagoreans, and they, you know, they had a kind of pseudo-mathematical religion. They did a lot of math, but it was really a kind of philosophy or religion. And part of this philosophy was the idea that everything was rational. Everything could be expressed as a ratio of these whole integers. And so then I forget what his name was, but some guy came up with this proof to show that square root of 2 is irrational, and the Pythagoreans just absolutely hated that. So they threw him off a boat into the Mediterranean and he drowned. So Yeah, somebody got killed over this proof. Okay, so this proof is both wonderful and also more complicated than any proof that we've seen so far, because it included an additional assumption about P and Q having no common factors, and we had to use this additional fact that the square of a number being even implies that the base of the square is even. We had to use that twice. And then what we ended up contradicting was this assumption that P and Q have no common factors.
So I have a question on that.
Yeah, sure.
So when we're dealing with more complicated proofs like this, will we be given certain information, certain facts that we won't have to prove, like that, like q squared? If q squared is even, then q is even, or will we have to prove some of those smaller facts inside of them if we're not giving them?
As we go along in this class, we'll accumulate facts that you can use without reproving them. For instance, things that I prove in lecture. So for instance, after this, now you can always use that square root of 2 is irrational in any future proof that you have to do. So yeah, you won't have to always reprove everything. And mathematics works by accumulation. So once you prove something, you don't want to be reproving it again and again and again, always.
Okay,
so we will kind of accumulate results that we can use. And in class, we proved a very similar result to this one, right?
Mm-hmm.
So, yeah.
Cool.
We've got 2 minutes left. Any more questions on this lovely proof? Another thing to notice here is that in our previous proof, well, in our first proof by contradiction, it could have just as easily been done by contraposition, right? Statements like n cubed plus 5 being odd implies n is even. You could have done that in a kind of more straightforward way using contraposition. Here, there's no proof besides a proof by contradiction. To prove that something is irrational, there's like no way to go about it besides like the only positive statement that you can do when you're dealing with irrationality questions is say, this number, like assume it's rational, and then see what that will imply. And it turns out that that implies something false. So that statement, square root of 2 is rational, had to also be false. Any further questions? If not, I'll let y'all go a minute early. I'm feeling magnanimous today. So we proved it was not rational to prove that it was irrational. Yes, exactly. What we really proved is we proved that if you assume that it's rational, then a contradiction ensues.
This makes so much more sense than when you first started like doing this.
Yeah, it takes, I think it's best to see some examples. Examples clarify the kind of abstract logic of it quite a bit, I think.
Yeah. All right. Well, thank you.
Yeah, absolutely. Have a nice day, everyone. Also, there are office hours today at 10:30 if anyone is interested.
Thank
Have a
you.
great day.
Yep.
Have a good day.
Have a nice day, everyone.
You.